Hello everyone, welcome to the lecture series of Engineering Mathematics 1. In this lecture series we are going to see partial differentiation. So here in previous lecture you have seen all the proofs of Euler's theorem, right? So we are going to see here in this lecture examples based on that proofs of Euler's theorem, means example based on the statement of Euler's theorem that we have seen. Okay, so here we are going to have an example. This is our first example. You can see we have to verify here Euler's theorem for the function u is equal to sin inverse x upon y plus tan inverse y upon x. Okay, so just let me choose a pen. Okay, so here first of all we are going to write always a given part u is equals to sin inverse x upon y plus tan inverse y upon x. Okay, now see here, I have to verify Euler's theorem. According to this, first of all I have to check whether this given function is homogeneous or not. Okay, तो इसके लिए सबसे पहले हमको यहाँ पर क्या करना है, put x equal to xt and y equal to yt, right? So we are going to put here, put x equal to xt and y equals to yt, right? So when I put here x equal to xt, what I get, see here, xt upon yt plus tan inverse yt upon xt. So you can see this tt get cancelled. So what I get here, yes, sin inverse x upon y plus tan inverse y upon x. This is our original function. You can check. This is given to us. That is the original function. So there is no term of t is remaining, right? So I can write this t as t raised to 0. Okay. So what I got here, when I replaced, see, u of xy, when I replace there x by xt and y by yt, what I got here, t raised to 0, again my original function back, means what is the degree here, 0, right? That is a representation of homogeneous function. Okay, so when you replace x by xt and y by yt, you must get your original function back with some term of t with power. It may have a power. Okay, so here t raised to n is what here, 0. Therefore I can write u is a homogeneous function of xy of degree n equal to 0. So here u is a homogeneous function of xy of degree n equal to 0. So I can write by Euler's theorem, if your function is homogeneous and it has a degree, then by Euler's theorem, what I can write? Yes, original statement we have to use here to verify. That is x into dou u by dou x plus y into dou u by dou y equals to n into u. But here what is the value for n? it is 0, you can see. So therefore, x into dou u by dou x plus y into dou u by dou y is equal to 0. So this first order relation is what? 0. Okay. So this is our equation 1. So by Euler's theorem, we got this relation x into dou u by dou x plus y into dou u by dou y, and value for this relation is 0. Right? And this we have to prove when we solve. Means when we differentiate this u with respect to x and with respect to y, definitely I should get a left hand side 0. Means I am now going to show here left hand side equal to right hand side. Okay. So to prove this, I am going to find the derivative of u with respect to x and y. Okay. So here differentiate u with respect to x, and now while differentiating with respect to x, we have to keep here keeping y constant. Okay, because u is a function of two variables, so this will give us a partial derivative, right? So here it is dou u by dou x is equal to derivative of sine inverse x. What is the derivative of sine inverse x? Yes, it is 1 upon under root 1 minus x upon y whole square into derivative of x upon y with respect to x, keeping y constant. It is 1 upon y. Okay, plus now derivative of tan inverse x. What is it? Yes, 1 upon 1 plus y upon x whole square into derivative of y upon x with respect to x. Y is constant and derivative of 1 upon x is, yes, minus 1 upon x square. Now this we have to simplify. So I can write here dou u by dou x is equal to, what I will get, see here? Yes, 1 upon y into 1 upon under root. If I cross multiply the terms, see here, solving this square, okay? If I do the x upon y whole square and then I cross multiply the terms, what I will get here, you can see, yes, y square minus x square upon y square, and this y square will go in numerator. So here I can write y square minus x square into this y. Okay, then this term x square plus y square upon x square, and this x square will go in numerator. So I can write here minus x square into y upon x square plus y square into 1 upon x square. Okay, now see here, I have to multiply this term by x because in our proof, our partial derivative dou u by dou x, it is multiplied by x. So multiply by x here. Multiply by x. I hope you all understood why I am multiplying this by x. So that will give me x into dou u by dou x equal to, see, this y get cancelled. So this will be x upon root y square minus x square minus, see, x square get cancelled, multiplied by x, so it will be xy, x square plus y square. Okay, so I hope you all understood. Let's say this is equation A. Okay, now I got a value for x into dou u by dou x. Now I want to find y into dou u by dou y. So what I have to do? Definitely I have to differentiate u with respect to y, keeping x constant this time. Okay, so differentiate u with respect to y, keeping x constant, right? So what will be the derivative of u then with respect to y? That will be a partial derivative. And what is your u? Sin inverse x upon y plus tan inverse y upon x. Differentiate this with respect to y now. So this time derivative of sin inverse, it is 1 upon under root 1 minus x upon y whole square into derivative of x upon y with respect to y. So x is constant minus 1 upon y square, right? Then it is what? Plus, right? And derivative of tan inverse y upon x. So it is 1 upon 1 plus y upon x whole square into derivative of y upon x with respect to, right, y. So 1 upon x is constant and derivative of y is 1. Just let's simplify this. So what it will give me? Minus x upon y square upon, see here, if I solve the denominator, that will give me y square minus x square, and this y square which will be a denominator will go in numerator. So into y square plus, now solving this term, if I solve, I'll get here x square upon x square plus y square into this 1 upon x, right? So here this x and this x will cancel, this y square and this y square will cancel, and I have to multiply this dou u by dou y by y. Why? Because here in our proof, our dou u by dou y is multiplied by y. Okay, so let's multiply by y here. Multiply by y. So what I will get? Y into dou u by dou y is equal to, if I multiply here by y, this will give me, yes, minus x into y upon under root y square minus x square, then plus x into y upon, yes, it is x square plus y square. Okay. Okay, here actually when we take a cross multiplication, y square from root, when it come out, that will be y only, right? So by mistake I have written here y square, that should be only y. So see here, there is a little correction in the example. Let me write, this is only y, so that will cancel only one y, means one y will remain as there, right? So here you have a y already, and now this y and y will get cancelled. So this will give you minus x upon root y square minus x square plus x into y upon x square plus y square. Okay, say this is equation B. So when I do the addition of these two equations, what happens? See, so when I do here addition of equation A plus equation B, okay, this is our equation A, you can check, and this is our equation B. When I add these term and these term, both are same but they are having opposite signs, so they are going to cancel. And these term and these term, these are also same but having opposite signs, so that are also going to cancel. So when I do the addition, what I get? X into dou u by dou x plus y into dou u by dou y is equal to 0, and hence verified, we can say. Okay, so whenever there is a homogeneous function, we don't have to differentiate the terms. We can directly write the relation of first order and second order and its values. Okay. So I hope you understood the example. Let's have the next example here. So see here, in this example, again this function is given to us and we have to show that x into dou u by dou x plus y into dou u by dou y plus z into dou u by dou z. First order relation. Now see, this time there are three variables x, y, z. Okay, so we can write Euler's theorem for n number of variables, not only for two variables x, y. Okay, if there are x, y, z and w, then also I can write a Euler's theorem for the four variables. Okay, just concentrate here. There are three variables, so now we have to think about only this. So first of all, finding the value for this first order relation, I have to check whether this given function u, it is homogeneous or not. If it is homogeneous, then only I can use Euler's theorem. Okay. Otherwise, what I have to do, I have to differentiate the term and I have to find left hand side, that will give me right hand side. Then showing left hand side and right hand side equal. Okay. So first of all, I am going to check here u is equal to, write down a given part. Okay. 1x square plus y square plus z square plus cos into xy plus yz plus xz upon x square plus y square plus z square. Okay. So first of all, before solving the example, what I have to do, I have to check whether this given function u is homogeneous or not. Then only I can, I can use a Euler's theorem. Okay. So how I am going to check? Definitely I have to put again x equal to xt and y equal to yt, and that should satisfy u of xt yd is equal to t raised to n u of xy. Right? So here put x is equal to xt, y is equal to yt. Okay. So u is equal to, when I put here x equal to xt, y equal to yt, see, x cube t cube into y cube t cube. I am replacing here x, y and z. See, z also I have to put zt. Okay. Then z cube t cube upon x square t square plus y square t square plus z square t square plus cos of xt yt plus yt zt plus xt zt upon x square t square plus y square t square plus z square t square. Okay. Now see here, in this, what is in numerator? Right. I can have here t cube into t cube into t cube. Means I can do the addition of the power. So what is it? Yes, t raised to 9 in bracket x cube y cube z cube upon, at denominator what I can find? Yes, it is t square x square plus y square plus z square plus cos of, here see, t into t, t into t, t into t means t square. So I can find here t square common, xy plus yz plus zx upon, here also t square is common. So what is remaining there? X square plus y square plus z square. Okay. Now here you can check this t square and this t square. This get cancelled. This is u equals to, okay. Let u equals to v plus w. So therefore v is equal to, see, t raised to 9 upon t square means t raised to 7 x cube y cube z cube upon x square plus y square plus z square, right? And w is equals to cos of xy plus yz plus zx upon x square plus y square plus z square. Okay. Now see here, this v is a homogeneous function of degree 7. But here no term is remaining for t, so I can write t raised to 0 outside, right? And this w is a homogeneous function of degree 0. So therefore here v is homogeneous function of degree n equal to 7 and w is homogeneous function of degree n equals to 0. So by Euler's theorem then, what I can write? If it is a homogeneous function, definitely. Now you have to check which is a homogeneous function. Here v and w are homogeneous functions, right? So first of all I am going to write for v. Dou x into dou v by dou x plus y into dou v by dou y is equal to n into v, that is equal to 7v, and x into dou w by dou x plus y into dou w upon dou y equals to n into u. But what is the value for n? 0. So it is 0, right? And now I have to show this. So this time I can consider a left hand side. So I can write here now left hand side is equal to x into dou u by dou x plus y into dou u by dou y plus z into dou u by dou z, right? But what is u? We have considered the u as v plus w. So I can replace here x into dou by dou x of v plus w plus y into dou by dou x of v plus w plus z into dou by dou x of v plus w, right? Now I can separate a derivative. So I can write x into dou v by dou x plus x into dou w by dou x plus, here also separate a term, y into dou v by dou x plus w into dou w by dou x, not w, this should be y, plus, now here multiply z into dou v by dou, I think this is, just a minute, by mistake I have written there, x, that should be actually y and z here, okay. So what I have to write here, it is dou v by dou z, here it should be y, and this should be z. Okay, so this must be y here, not x. Okay, then plus this is z into dou w by dou z, right? So v and w we are going to separate. So I can write here x into dou v by dou x plus y into dou v by dou y plus z into dou v by dou z plus x into dou w by dou x plus y into dou w by dou y plus z into dou w by dou z. Okay, and what is the value for these? X dou v by dou x plus y dou v by dou y plus z dou v by dou z. We have already find here, it is 7b. So I can write this is 7b plus, and what is the value for this? This also we have find here. What is it? 0. So I can write here it is 0. That is equal to 7 into, what is v? Yes, we have a value for v, this one. Okay, so now this time we don't write this t raised to 7 because this we have taken just to check whether the given function is homogeneous or not. Okay, this is our consideration, our substitution. Okay, so we are not going to consider that value for v. Just we have to write here x cube y cube z cube upon x square plus y square plus z square. Okay, so I hope you all understand, and hence proved we can say. Hence proved. This is our required proof. Okay, I hope you all understood the examples that I have taken till now. Let's have one more example here. Now this is the example. U is equal to tan inverse x cube plus y cube upon x plus y, and we have to prove that x into dou u by dou x plus y into dou u by dou y is equal to sin 2u. And for second order relation, it is 2 cos 3u into sin u. This we have to prove. Okay. So always remember, before solving example, we have to always check whether given function is homogeneous or not. And how we are going to check? Yes, we have to put there x is equal to xt and y is equals to yt. Okay. So here, first of all, we have to write down our given function. What is it? U is equal to tan inverse x cube plus y cube upon x plus y. Okay. So here what we are going to do? We are going to put x equal to xt and y equals to yt to check whether given function is homogeneous or not. Okay. So when I replace here x by xt, it is x cube t cube plus y cube t cube in numerator, and in denominator it is xt plus yt. Okay. Now see here what I can write. Tan inverse t cube taking common, what is remaining? X cube plus y cube upon, and in denominator what is common? T. What is remaining? X plus y. Right? So this gives me tan inverse t cube upon t, means it is t square, and original function is x cube plus y cube upon x plus y. Okay. But when I replace here x by xt and y by yt, I should get the form t raised to n u of xy. Right? But here see, I cannot take this t square outside this tan inverse, right? So I am not getting this required form. To get this required form, what I have to do? I have to shift this tan inverse on the left hand side of this term. So if I do so, if I transfer this tan inverse on the left hand side, that will be tan u is equal to t square. And what is the original function? X cube plus y cube upon x plus y. Right? So now this time I can represent the function in this format. But which function? Tan u, not u. Okay? So therefore, f of u is equal to tan u is homogeneous function of degree n equals to 2. Okay? Now tan u is homogeneous, means f of u is homogeneous, and when f of u is homogeneous, we have first order relation. Therefore, by Euler's theorem, first order relation, x into dou u by dou x plus y into dou u by dou y is equals to n into, yes, f of u upon f dash of u. This result we have to use because f of u is homogeneous, not u is homogeneous. Okay? So whenever your f of u is homogeneous, you have to use only this formula for first order. Okay? Now, putting here values. What is our f of u? Yes, it is tan u. So, and what is your n? It is 2. So that will be tan u upon. Now f dash of u means whatever is your f of u, you have to differentiate with respect to u. So what is the derivative of this f dash of f of u? F dash of u is equal to, yes, it is sec square u. Okay? Derivative of tan, it is sec square u. So here, what I will get? Therefore, x into dou u by dou x plus y into dou u by dou y means value for this first order relation I got 2 into tan u upon sec square u. So I can write here 2 into tan u, that is I can write sin u upon cos u. Okay? And sec square, I can write it is cos square u. So one cos get cancelled. So it is 2 sin u cos u, that is a result of sin 2u. Sin 2 theta, I can write 2 sin theta cos theta. I have to use that result here. Okay? Now see here, I can keep my answer till this also. But they have asked me to prove what? First order relation is equal to sin 2u. So I have to do this necessary adjustment there to find the required proof. Okay? Now, by second order relation for f of u homogeneous, what we have? Now, we have by Euler's theorem, when f of u is homogeneous, second order relation, value for second order relation, what is it? Yes, y square dou 2u upon dou y square is equal to, very good, it is g of u in bracket g dash of u minus 1. Where? What is g of u here? It is n into f of u upon f dash of u. Right? So, therefore, g of u is equal to, n is what? 2. Right? Now, f of u, it is tan u, g of f dash of u, है ना? It is what? Sec square u. So I get here 2 sin u upon cos u into sec square u, that I can write cos square u. Get cancelled, and it is what? Yes, not 2, it is sin 2u. Okay, right? So I have to use here this value of g of u. G of u is what now? Sin 2u. Okay, so here from this, can I find g dash of u? Yes, what is the g dash of u? Derivative of this sine. And what is the derivative of sine? It is cos 2u into 2. Okay, so I hope you all understand. Therefore, I have a value for second order relation x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equal to, put the value for g of u. Yes, it is what? Sin 2u into, what is the value for g dash of u? Yes, it is 2 cos 2u minus 1. Now just simplify the term. So that is 2 sin 2u into cos 2u. Can I here write directly the formula? Sin 4u minus sin 2u, because 2 sin 2u cos 2u, 2 sin theta cos theta, that is sin 2 theta. Using this result here, I can write sin 4u. Okay, now here sin a minus sin b, according to that it is 2 cos a plus b upon 2, means 4 plus 2 6, 6 by 2, so it is 3 into sin a minus b upon 2. So here 4 minus 2 upon 2 means 2 upon 2, that is 1. So I can write here only sin u, and which is my proof, required proof, 2 cos 3u into sin u. So I can write here hence proved. So this is how we can use Euler's theorem to solve or to find first order relation or second order relation. Okay, value. Okay, so here this is our next example. To solve this, again we are going to use the Euler's theorem. So we have to find a value for this second order relation. Now here see what is the difference between previous question and this question. Here they ask to find us a value, not prove that. When they ask you to prove, you have to do necessary adjustment here to find your required term. Okay, but if they ask you to find only the value, means you can just simply use a formula, put the values and leave it. You no need to solve further. Okay, so let's solve this example here. First of all, definitely we have to write here given part. So what is the given part here? U is equal to cosec inverse root x raised to 1 by 2 plus y raised to 1 by 2 upon x raised to 1 by 3 plus y raised to 1 by 3. Okay, now see, actually how to check whether a given function is homogeneous or not, I told you in previous examples. Now here in this example, I am going to tell you a shortcut how to check whether a given function is homogeneous and what is its degree, if it is homogeneous. Okay, so you have to check all the terms that are in numerator. You have to check are all powers of that variables are same. Yes, you can see x raised to 1 by 2, y raised to 1 by 2. Whatever the terms in numerator, all are having same power. And also in denominator, all are having same degree. So whenever there is a same degree in numerator as well as in denominator, okay, then we can say it is a homogeneous function. But now I have to find a degree of this homogeneous function. So see here how we can find. See, 1 by 2, 1 by 2 means in numerator it is 1 by 2 and in denominator common degree it is 1 by 3. and I have to subtract this 1 by 2 minus 1 by 3. So when I do this, its LCM is 6, right? So it is 3 minus 2 means 1 by 6. Okay, but it is in square root, means I have to multiply this term by 1 by 2. Okay, so that will give me 1 by 12. I hope you all understand. Your powers are multiplied by 1 by 2. So that's why I have to multiply this calculation by 1 by 2. Okay, because that are in square root. So here this is the degree. N is equal to 1 by 12 for the given function. So I can write, but not cosec inverses. Okay, cosec u is homogeneous here, not u is homogeneous. So I have to write cosec u is homogeneous function of degree n equals to 1 by 12. So therefore, by Euler's theorem, now see, cosec u is homogeneous means f of u is homogeneous, and therefore by Euler's theorem, when f of u is homogeneous, okay, not u, f of u is homogeneous. So when f of u is homogeneous, what is the value for second order relation? Yes, x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equal to g of u in bracket g dash of u minus 1. Okay, so here I have to find this term where g of u is equal to n into f of u upon f dash of u. So what is n? It is 1 by 12, right? What is f of u? Cosec u. Okay, and what is the derivative of cosec u? It is minus cosec u into cot u. So cosec u get cancelled, and 1 upon cot u I can write minus tan u upon 12. Okay, and if I differentiate this with respect to u, that will give you g dash of u. So what is the derivative of g dash of u? Derivative of tan u, it is minus sec square u upon 12. Okay, and simply you have to put the values of g of u and g dash of u here in this suppose equation 1. So I can write from equation 1 x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equal to, simply you have to put the values of g of u and g dash of u. So I can write that is equals to, what is the value for g of u? Yes, it is minus tan u upon 12. So I can write here minus tan u upon 12 in bracket g dash of u minus sec square u upon 2 minus 1. Multiplying by minus sign, that will give you tan u upon 12 in bracket sec square u minus going to be plus upon 2. That is the required answer. Okay, just they are asking us to find the value, not to prove. So simply put the values of g of u and g dash of u. That will be your final answer. No further steps you have to do here. Okay, so I hope you all understood the example that we have taken here. Okay, now let's have one more example on this. Now this time we have to find the value for this second order relation where function is given to you this. So write down your given part first. So what is given here? U is equals to sine inverse x cube plus y cube bracket raised to 2 by 5. Okay. So you can check in numerator what is the common degree? 3, and it is multiplied by 2 by 5. So 3 into 2 by 5, it is 6 by 5. That is a degree of your homogeneous function. But who is homogeneous? Not u. Your sine u is homogeneous. Okay. So here, therefore, sine u is homogeneous function of degree n is equals to 6 by 5. Okay. So therefore, by Euler's theorem, what we can write? Yes, here sine u homogeneous means f of u homogeneous, and when f of u is homogeneous, for second order relation we have a result. Yes, it is what? 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equals to g of u in bracket g dash of u minus 1. That is actually the formula. Where? What is g of u? Yes, it is n into f of u upon f dash of u. Okay. So what is n here? Yes, it is 6 by 5. What is f of u? Yes, it is what? Sine u, because sine u is homogeneous. And what is f dash of u? Derivative of sine u. It is what? Cos u. So sine u upon cos u, it is tan u. So I can write here 6 by 5 tan u. That is the value for g of u. Similarly, now here I can find g dash of u. So therefore, g dash of u is equals to 6 by 5 sec square u. Okay. So I hope you all understand. We got the value for g of u and g dash of u here. Putting this value here in suppose this equation 1. So what I can write? Therefore, from equation 1, x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equal to g of u. What is g of u? Yes, it is 6 by 5 tan u. So I can write here 6 by 5 tan u. Then what is g dash of u? It is 6 by 5 sec square u minus 1. Right? And they just ask us to find the value. So we can leave here also. We don't have to solve further. As I told you already. Okay? I hope you all understood the example. Okay? So here, this is how we solve these examples using Euler's theorem. Okay? So you have to check whether your function u is homogeneous or f of u is homogeneous. Okay? Then only you can decide which formula you have to use. If u is homogeneous, you have to use a result of n into u for first order and n into n minus 1 into u for second order. But if f of u is homogeneous, then for first order relation you have to use n into f of u upon f dash of u, and for second order relation you have to use g of u in bracket g dash of u minus 1. Okay. So I hope you all understood the example. Thank you for watching this video.